Hello everyone, so this is the third video in our playlist, and in this video we are given with a problem and we're asked to show that the fanning friction factor is equal to 16 over Reynolds number for a laminar flow. We should either find that using a cylindrical control volume with either a pressure drop or a vertical elevation. So I want to work with the vertical elevation, so we're not gonna there are two ways to do it. So we can either do it horizontally and consider pressure, like change in pressure, or we can either do it horizontal, like vertically, and consider the gravitation driven flow. So I want to do it with using a gravitation. So let's imagine we have a tube. And the water column, like the liquid column, is driven inside, right? So how we can imagine that is, let's imagine we have a tank, right? So it has some fluid going out, right? So that's going to be our just tanks, and the pressure here is 1 atmosphere, can be 1 atmosphere, and the pressure here should also be 1 atmosphere. And this is not a rho GH case because we're not in a closed system, right? So we're gonna do, we don't need that now. So we're gonna consider this tube and we're gonna do a force balance for our specific case. For this case, we know that there is a weight of a liquid column, right? And there's also delta Z, which is the height, which is the kind of length of a. We can say that it's a negative length because it's going from up to down. So delta Z is kind of referred as a negative length of a pipe. Okay. To do a force balance, the first force we have is the weight of a water, like the liquid column, right? And the weight is, as we know, it is mass times the gravitational acceleration, and the mass itself is the volume times the density of a liquid, right? So what we have is the density being multiplied by, so if we consider the volume of a pipe, that's going to be 4 pi pi r squared. Yep, yeah, that's pi r squared and times delta z. Yep, delta z because we're considering a change, right? So the length, like the cross-sectional area being multiplied by the length. Okay. What we have next is the shear, what we have next is the shear stress being multiplied by the cross-sectional area, which is it's not a cross-sectional area, but the shear stress with the surface area, which can be referred as 2 pi r or times the delta z. So it's like the stress, like friction force on a wall. Okay, our delta z's are gonna get cancelled, our pi's are gonna get cancelled, and r, so we're gonna be left with 1 r in the first side, and our shear stress itself is the viscosity times change in velocity over change in radius, right? So if I want to write that equation, what I'm going to have is viscosity. So I can make that equal to negative rho r, and that's going to be divided by this 2, and we can also divide that by viscosity here. So this is our how the velocity of a this is how our velocity of a fluid is changing over the radius. Okay, if I want to take the integration, so if I integrate that, I'm going to get the velocity And what I'm gonna have is gonna be rho r. It seems like I forgot something. Oh yes. So this thing here was the volume, right? And I forgot to multiply it by g because the weight is rho g a. Like mass times the no, it's not a volume. This is the volume. This is the volume. This is the mass, and mass times g, mass times the gravitational acceleration is our weight. So rho g over 2 viscosity times r squared over 2, right? And that's gonna be plus c because we're integrating it, right? And in order to find plus c, like the constant, we know that the velocity, like in the wall, like an other wall, is gonna be equal to 0, right? So we can find that using this equation. So when it's equal to the capital R, it should be equal to 0. So our C is going to be equal to rho g r squared over 4 mu, right? Viscosity. So I'm going to plug that back. So my velocity equation now is going to be rho g over 2 viscosity, and that's going to be r squared minus capital R squared minus r squared. Yep. Okay, what's next? So that's our velocity, right? So now we also can find the flow rate of our equation. So the flow rate is going to be equal to the velocity times the change in like area, change in the area. And if we want to integrate that, we're going to use the spherical shells concept. And what we're going to have is like velocity integrated over 2 pi r, and that's going to be dh. No, it's going to be the radius. Yes, so if you want to integrate that, first, before the integration, we have to plug this back to our velocity, right? So what we're going to have is, with the integration, we're going to have 2 pi outside, rho g outside, and we're going to integrate that from the 0, from the center to the outer shell. Yep, we shouldn't forget that. Yep, 2 mu, okay, 2 mu, right? And then that's being integrated. So what we have for the integration is we have this r, so it's going to be just r squared over 2 and minus r to the 4th over 2, and the whole thing is being integrated from 0 to r, right? And when we're plugging when we plug 0, that's going to be, everything is going to be equal to 0, right? So we're left with only like everything plugged in the capital R, like the radius and outer shell. So it's going to be 2 pi rho density times gravitational acceleration over 2 times viscosity. I think I forgot something. So yes, when I was doing this step, I forgot to multiply it by 2. So this thing is going to be 4. This is going to be 4. And yep. So the equation we're going to have is going to be this is gonna get cancelled, so 2 times r to the force 2 minus r to the r to the 4, so this is also 4, this is r to the force over 4. Yes, so that's what we are gonna have. And if I want to write that q separately, that's gonna be this inside is going to be r to the force over 4. So the equation for the flow rate I'm going to have is pi rho g over 8 mu r squared, right? And if I want to write r squared, oh no, r to the force, sorry. R to the force is equal to the diameter over diameter to the force over to the 2 to the force, right? So what I'm gonna have is q is gonna be equal to pi times the density times the gravitational acceleration over diameter to the force over no, it's and that's 4 to the squared, so I'm gonna have 128 times the mu. Yep, that's the equation I have for the flow rate. And the next thing I can do here is okay, I'm gonna consider the Bernoulli equation. So the Bernoulli equation was like change in P over density plus change in velocity squared over 2 plus g times z2 minus z1 equals negative frictional heating, right? Okay, our pressure, our flow is not driven by the pressure, right? So that's going to be equal to 0, and this is also going to be equal to 0. So we're going to consider only this part, right? And as we were saying, our delta z is negative change in negative length. So when we can kind of write that as negative L. And from this equation right here, I can solve for g, right? So what I'm going to have is 128 mu times q over pi rho g, g to the fourth, right? And I can get that g and plug into my Bernoulli equation. Okay, what I'm going to have is, so let me copy this. Paste it here. So what I'm going to have is the whole thing. Okay. G times L. So I said that it is negative L so that I can write it as just the frictional heating. So negative cancels out each side. And then, yeah, so that's what we're going to have for our equation of frictional heating, right? Okay, so the next thing we want to do is, so in the question we're asked to find the fanning friction factor for the laminar flow. And this is only valid in laminar flow, right? So usually in some textbooks, they're going to express this frictional heating as F, which is the fanning friction factor, like it's 4F times delta X over D times V squared over 2. Okay, so that's how they express the friction heating, where this is the fanning friction factor. And in the question, we want to prove that finding friction factor we have is 1 over Reynolds number. So what is that? What that is, so here I have a Moody diagram, so which is like chemical engineers use. So kind of for the laminar flow, the coefficient of like fanning friction factor is always equal to 1 over Reynolds number, and it's not applied to the turbulent flow. Okay, so if I want to do that, I can make these two equal to each other, right? So I'm going to have 128 mu times the like viscosity times the flow rate times L over pi density times the diameter to the force is going to be equal to 4F delta X V squared over D times 2, right? And I know that the delta X is equal to our length, right? And what else is going to be canceling is, so I'm going to be canceling the diameter, so we're left with diameter to the cubed, right? Okay, what else we're left with is, so this is going to cancel, this is going to be 2, and this is going to be 64. So my friction factor is going to be equal to, so this thing, 64 times viscosity times the flow rate over pi rho times diameter to the squared over velocity squared. Yes, and my flow rate itself is equal to the velocity squared, velocity times the cross-sectional area, which is pi d squared over 4, right? So I'm going to plug that back to my equation. So my fanning friction factor is 64 mu, like the viscosity times pi rho d to the cubed velocity squared times velocity pi d squared over 4. So that is, so the velocity cancels, so we're going to left with velocity, one velocity, so pi is going to cancel, diameters cancel, so, and this is going to cancel also. So what I'm left with is 16 times viscosity over rho times diameter times the velocity, right? Okay, this seems to be very familiar. So we know that the Reynolds number is equal to the density times the diameter times the velocity over the viscosity, right? It is exactly this opposite, right? So which means my friction factor is equal to the 16 over Reynolds number, which, so in this question, we're asked to prove that finding friction factor for the laminar flow is 16 over Reynolds number, which we proved. So in this question, we started with the gravity-driven flow, like the vertical gravity-driven flow, where the pressure change is, where there's no pressure change, and using the frictional heating equation and the Bernoulli equation, we derived that the fanning friction factor for the laminar flow is going to always be equal to 16 over Reynolds number. Thanks for your attention.